Hi, I'm Franck Michel from Université Côte d'Azur, CNRS and INRIA in France. This video is a replay of a presentation I gave in December 2025 at KCAP, the Knowledge Capture Conference. And the title goes like this: Q²Forge Mining Competency Questions and SPARQL Queries for Question Answering over Knowledge Graphs. So I'd like to start this presentation with a few words about what it takes to make a knowledge graph reusable. As you know, there are lots of public knowledge graphs available on the web. You can get them from the linked Open Data Cloud or from data portals. And usually they come with metadata-based description that includes the authors, the date of publication, the title, maybe keywords, the domains that pertain to a license, and so on and so on. And usually these metadata are sufficient to enable a certain degree of fairness, but when it comes to actually reuse a knowledge graph, you need more than that. And what you would typically like to get is a set of competency questions, that is, natural language questions that will give you an idea of the questions that the graph can help you answer. But also, that's not the only thing. You would like to get a description of the data model, that is, what are the ontologies that are being used in the graph and how they are used. And ideally, that would come with also SPARQL queries, example SPARQL queries, because as you know, it's much easier to start from existing SPARQL queries and adapt them than crafting new ones from your own. And typically, you will also need to translate competency questions into SPARQL queries. And as you know, this requires a double expertise, one which is about the domain of the knowledge graph itself, and the second one, which is about SPARQL and semantic web technologies in general. So if you don't have all of that, you would typically start exploring the knowledge graph with prototypical SPARQL queries to figure out what's in the data. And that will give you a fair idea of what's in the graph. And from there, you will try to start figuring out some questions that experts would like to ask about this knowledge graph. And then you will need to translate those questions into SPARQL, but that's quite a time-consuming task. So you will decide to train or fine-tune maybe a language model to do that for you, that is, translate a natural language question into an accurate SPARQL query. But to do that, to train, to fine-tune this model, you will need more examples of query and question and query pairs. And the problem is that there are quite little such datasets of question and query pairs, and they usually have a rather limited scope. That is, they often pertain either to DBpedia or Wikidata, but they are not necessarily adaptable and applicable to any kind of knowledge graph. So to address those issues, we have designed a framework that we call Q²Forge that seeks to address several goals. The first one is to create datasets of question and query pairs, that is, a natural language question and equivalent SPARQL query pairs that we call Q2 sets, and the Q2 in Q²Forge stands for question query. So you can read it as question query forge. Q²Forge also seeks to address several use cases. The first one would be if you're a knowledge graph publisher, you could use Q²Forge to document your knowledge graph, first of all with competency questions, but ideally also with SPARQL queries, example SPARQL queries that may or may not be the equivalent of the competency questions that you provide. As a knowledge graph consumer, you would typically use Q²Forge to help you formulate queries and translate existing questions that you have into accurate SPARQL queries. And if you are developing a query answering system, you would typically use Q²Forge to train and benchmark translation models or conversational agents and so on. And again, to do that, you would need datasets of question query pairs. Finally, Q²Forge is a framework, but it's also a pipeline, and we intend to make this pipeline generic. That is, it would be able to be applicable to apply to any kind of knowledge graph, or any kind, at least RDF knowledge graph with a SPARQL endpoint, but in any kind of domain. It should be extensible. That is, there are some predefined steps in the pipeline of Q²Forge, but you could add your own steps or also replace existing steps with your own implementation. The pipeline is also end-to-end, that is, it goes from the creation of a competency question to the creation of an equivalent SPARQL query, its execution and refinement. But pipeline also intends to be flexible. That is, you're not locked into a whole pipeline from which in which you need to go from the beginning to the end. You can pick up just one of the tasks in the pipeline, execute it with your input, get the output, and do something else with that. And basically, Q²Forge implements three main tasks that are all assisted by language models, may they be large and small, or small, this is configurable. The first one, like I said, will be to create competency questions. The second one will be to translate questions, possibly those competency questions or some other questions that you have, into counterpart SPARQL queries. And the last task will be to verify and refine the SPARQL queries that have been generated. So now I'll present the different steps of the pipeline. So the first step will be to create a knowledge graph configuration where you will provide some minimal information about the target knowledge graph. That would be a name, description, SPARQL endpoint, the namespaces and prefixes that you would like to use in the SPARQL queries. Typically, there are also some additional parameters that are not configurable through this interface, but through the backend directly. And these pertain typically to the language models that you would like to use in the different steps and how you assign those models to each and every step of the pipeline. Once we have this configuration, we will start with doing a bit of pre-processing that we will extract some important information from the knowledge graph. And typically that will consist in extracting a textual description of the classes and properties that are being used in the knowledge graph. And we will use that later. The second step will be the first real big task that you would be interested in, which is the generation of competency questions. So here we'll generate the competency questions and optionally export them for use with another tool. And here is how the interface looks like. So basically we will prompt a language model, providing it with some information that you have already given in the knowledge graph configuration, and you can edit it, of course. That will also contain the use ontologies that are extracted from the knowledge graph and typically using the VOID annotations. And there are also an additional free input field where you could put any kind of thing that seems relevant for the model to be able to generate accurate competency questions. So typically, if you have published an article that describes the knowledge graph, that's typically where you would paste the abstract of the article so that you will guide the model through the description of the graph, of the entities it contains, and help it provide and generate more accurate competency questions. Once this is done, you will choose a model, number of questions, and run and submit the whole prompt to the language model. And if everything goes well, it will reply with a JSON formatted answer like this one. Each question comes with a complexity level, which could be basic, intermediate, or advanced, and a few tags that qualify the domain of the question. Once you've that, you can either export the set of questions for use in another application or save them locally in your browser, typically in a cookie. And when you do that, you can then move on to the next step, which will be the actual generation of the SPARQL query, not only generation, but also the execution and the interpretation of the SPARQL query results. So here, Q²Forge relies on various scenarios that are provided by the backend. And here I need to get into a bit more details. So here is one of the scenarios that we use. Here, typically the user would fill in a question that can be one of the competency questions that has been generated in the previous step or another question. So there is a first step, which is a basic validation where we just ask a model to make sure that the question that is being asked is relevant with respect to the graph. So that's a very basic step. And if that's the case, then we will go on with the pre-processing of the question. So here, there are quite a few things that happen. In the pre-processing, we will first extract named entities from the question. And from there, we will try to extract the related classes. That is, the classes the ontology classes that are similar to the named entities in the text embedding space. And this is why in the pre-processing step, I mentioned that we need to do this pre-processing of computing the text embeddings of the classes. So using this similarity measure, we will select the classes that seem to be the most relevant to answer the question. And then we will try to figure out how to represent the classes. That is, not only just take the ontology definition of class, but how they are actually used in the knowledge graph, which might be very different from the actual definition of the ontology itself. So here we have different options that can be serialized in natural language as tuples in a turtle-like syntax. So we can experiment with these different syntaxes. And the last thing that we will do in this step is to select possibly existing example SPARQL queries. So I didn't mention it, but with the knowledge graph configuration, you can also provide a few example SPARQL queries, and that's generally very effective to guide the model through the generation of an accurate SPARQL query. Once we have retrieved all of that, the classes and the possible example SPARQL queries, we will now create a prompt that will instruct the model to generate an equivalent SPARQL query, and we'll submit this prompt. So here, there are few possibilities. So first, we will verify that the answer contains an actual query that is just at least a syntactically correct SPARQL query. And if not, we have a retry mechanism. If there is a query, we will try to run it, that is, submit the query to the SPARQL endpoint, get the result, and ask a model, again, to interpret the results. So here is how the user interface looks like. So here you can see the different steps of the diagram I just showed that are streamed back to the user interface. And if everything goes fine, you will in the end get a SPARQL query like this one. And if it gets even more fine, you will get an answer to the SPARQL query, and the model will interpret the answer and provide you with a natural language answer. Okay, so that's all fine. But to be honest, quite often this is not the way it works, because either the query is not right or not good enough, maybe it lacks a few triples, or maybe it adds triples that shouldn't be there, whatever. There are plenty of reasons for which it might not work, and it might return zero result typically. So to go ahead with that, you have here another button, Refine. And this Refine button takes you to the last step of the pipeline, which is about refining the SPARQL query. So here we will refine and judge the query. I will explain this. So here is the interface. The first part of the interface is basically a SPARQL query editor. Here, this is YesGUI, if you know it, where you could just edit whatever you like in the query and submit it to the endpoint and check the results and do it again, and so on. Okay. Now, the problem is that quite often ontologies contain terms, may they be classes or properties, that are very opaque. Typically, if you use OBO, you have these OBO IAO000115 and so on. You don't know what that means, and that's the case with plenty of OBO ontologies. So here we have another part of the query of the interface that will retrieve those textual descriptions of the classes and the properties to help you make sense of the query that has been generated and make sure whether it's good or understand if something has not been used in the right way. And lastly, we have a judge step. So here, you will typically use a language model. Again, you select the language model here of your choice, and you will use it to judge the relevance of the query that's been generated with respect to the question. So we will prompt the language model and ask it to be critical about the query, its relevance to the question, and provide some hints for improvements. So this is the end of the main steps of the pipeline. And so far, we have run two preliminary experimentations with two quite different knowledge graphs. The first one with genomics has 27 million triples. The second one is about metabolomics, and it has 36 billion triples, so it's much bigger. And here, the table below gives you a few figures about the number of classes in each of the graphs, the number of properties, the time it takes to compute the text embeddings of the classes in the preprocessing step, the time it takes to generate some competency questions, to translate competency question into a SPARQL query, and so on. So those figures are, of course, only for information purpose, because they largely depend on the hardware that you're using, but not only that, also on the language models that you have chosen for each of the different steps. So starting from the empirical experimentations, we have already considered the next steps that we want to go through. And those next steps will take place in the context of the metabolomic AI project, whose goal is to analyze and interpret metabolomics data by combining knowledge graphs with AI and machine learning techniques. And among those next steps, what we want to do, of course, is to run a much larger scale experimentation to assess different things. First, the relevance and the accuracy of the questions, the competency questions that are generated, and the SPARQL query counterparts of the questions, and the relevance of the pairs. Also, we want to be able to assess the effectiveness of the different approaches, the RAG approaches that we are using. So, like I said, we provide the model with a set of relevant classes, how to select those classes. We provide it with a serialization of the classes to describe them and give the model an idea of how they are used in the graph. So how to serialize those. So all of these, there are multiple options each time, and we need to have a much more exhaustive experimentation to assess all of these different techniques and which one works best in which situation and so on. We also want to investigate the follow-up interactions. That is, for now, we create a set of questions, and from one question we create a query and we execute it and we refine it. So we would like to have something which is much more a follow-up dialogical interaction between the user and the interface. We also intend to explore what it takes to present appropriate visualization of the SPARQL results. Like I said, for now, we just provide a textual interpretation of the results, but sometimes text is not the most relevant. Maybe sometimes you need a graphics of some time, you need a map or any other kind of visualization. So there are lots of things here to do to automatically select the most appropriate visualization technique. We also want to explore what it takes to generate not only SPARQL queries, but federated SPARQL queries. That is, SPARQL queries that will be able to span multiple knowledge graphs at the same time. And finally, we intend to experiment with agentic interactions with knowledge graphs. So here I will just give you a hint of what that means. For now, this is how it works. So you have a user agent that connects to the web interface, and the web interface uses an API to invoke the different services that are provided by a backend. And those services are the creation and activation of a configuration, the generation, it can ask for the generation of competency questions, or the translation of a question to SPARQL, judge question, and so on and so on. What we want to do is to make this available not only to a human user, but also to an AI agent by means of an MCP server that publishes the services of the API. And as a matter of fact, we have a very early stage proof of concept to evaluate this. So we have published those API services as an MCP server, and now we are using this Drive AI tool to ask a few questions. So here, imagine we are in the place of an AI agent, and we ask what are the available knowledge graph configurations, and the agent selects automatically the right tool to get the list of the configuration. And then we ask to generate 4 competency questions on one of the knowledge graphs that has been configured. And here, after a first failure, they'll first try to generate the questions, but it doesn't work until a knowledge graph configuration has been activated. So it figures this out the second time, and the second time it doesn't activate config, and it asks to generate the number of the 4 competency questions that we have asked. So again, this is a very early proof of concept, but still it seems to be promising, and this is the kind of thing we will to explore in the context of this metabolomic AI project. So as a conclusion, here is the link to our GitHub repository where you can find the code. Everything is open source. And just to remind the main goals of Q²Forge, it is to generate, test, and refine datasets of natural language question and equivalent SPARQL queries. It is RAG-based, it is domain agnostic and knowledge graph agnostic. That is, you should be able to use it with almost any kind of knowledge graph in any kind of domain. It's modular and extensible. And thank you for your attention.